Welcome to my videos on maths, statistics, physics, and chemistry. My first video is going to be on Calculus 1, the precise definition of a limit. So let's state the precise definition of a limit then. Let f of x be a function defined on an open interval containing some number a, except possibly at a. We say L is the limit of f of x as x approaches a, written as the limit as x approaches a of f of x equals L, means for every epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus a is less than delta, and obviously this being distance greater than 0, then the absolute value of f of x minus L should be less than epsilon. So what does this mean then graphically? Suppose this is our function f, defined on some open interval containing some number a. So we say L is the limit as you approach a, either from left or from right. If we can find some number, very small delta, such that when you are within delta of a, you must be within epsilon of L. So the closer you get to a translates into the closer you get to L on the vertical axis. So when you approach a from left or from right, you are approaching L from either coming from down going up or from up going down. So the idea of the limit emphasizes on the concept of closeness. How close can one get to a so that it is guaranteed that they are within epsilon of L on the vertical axis? So let's look at an example then that applies the precise definition of a limit. Use the precise definition of a limit to prove that the limit as x approaches 1 of 3x plus 2 is equal to 5. So in order to prove this using the precise definition of a limit, it is necessary at this stage to recap the precise definition of a limit. So here is our proof. And our precise definition of a limit says if the limit as x approaches a of f of x is equal to L, it means for every epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus a is less than very small number delta, and this being distance, you want the distance to be positive, then the distance between our function f of x and our limit should be less than epsilon. That's the precise definition of a limit. Now let us put our limit, our question into the precise definition of a limit as follows. Therefore, the limit as x approaches 1 of 3x plus 2 is equal to 5 means for every epsilon greater than 0, there exists a delta greater than 0 such that if the distance between x and 1 is less than delta, obviously distance must be positive, we had to take the 1 to the left here to obtain x minus 1 within the absolute value, like we did here on the precise definition of a limit when we took a to the left to obtain this part of the condition. So the limit as x approaches 1 of 3x plus 2 equals 5 means for every epsilon greater than 0, there exists a delta greater than 0 such that if this condition is true, then the distance or the absolute value between our function 3x plus 2 and our limit 5 should be less than epsilon. If this condition is true, then that must be true. So we set out to find a very small number delta such that if this condition is satisfied, then that one automatically follows. So we execute 4 steps here in our proof. Step 1, we state what is given, and that is epsilon is greater than 0. In step number 2, we look at the choice of our delta, which at this stage we do not know what our delta should be. That will make this condition true. If that is true, our third step is to suppose or assume that this condition here holds. Then we'll move on to the fourth step, which will help us determine what the choice of our delta should be. So we notice, what do we notice? We notice that this part here simplifies to something. 3x plus 2 minus 5 is exactly equal to 3x 2 minus 5 is minus 3. Factorizing the expression within the absolute value, we get 3x minus 1. And this means the absolute value of 3 times the absolute value of x minus 1. And the absolute value of 3 is 3 times the absolute value of x minus 1. It's important to notice at this stage that we said over here that x minus 1, the absolute value of x minus 1 is less than delta. So if we substitute delta here, everything we get must be less than 3 delta. So this is now less than 3 delta. At this stage, we set 3 delta to be equal to epsilon. Solving for delta, we get epsilon over 3. So this is actually the choice of our delta. So if we take epsilon over 3, substitute here, we're going to get exactly 3 times epsilon over 3. And if you cancel these two, you're going to get epsilon. Basically, this should be the end of our proof. Because what we're saying here is that if we take this expression, which is the choice of our delta, and substitute in that condition, that place there, and simplify this, it gives us this, which means that this expression here, which simplifies to that from up here, simplifies to that, is less than epsilon, because this gives us epsilon after simplifying it here. But let's see if this is correct. We check. And how do we check? We check the condition there. That if our choice of epsilon is correct, this one here, when we place, if our choice of delta is correct, which is epsilon over 3, when we place this expression, which represents delta, into that position, we must get this after manipulating that. If our choice of delta is correct, then this condition should give us this condition. So let's try to do that. So checking, not necessary, but we have to do it so that you understand that it is critical that you do the checking sometimes to just make sure that what you're doing is correct. What are we checking? We're checking that the absolute value of x minus 1 is less than delta, and our choice of delta is epsilon over 3. Now this is distance, so we can ignore the first part because distance is always positive. So this implies that x minus 1, absolute value of x minus 1 is less than epsilon over 3. Multiply both sides by 3, it simplifies to 3 times x minus 1, which is less than epsilon. The 3 cancels on the right hand side. Multiplying out, because the absolute value of 3 is 3, so this gives us 3 open brackets x minus 1 less than epsilon. Expanding the expression inside the absolute value signs, we get 3x minus 3 less than epsilon. At this stage, it's absolutely critical that you notice that minus 3 is actually 2 minus 5 less than epsilon. So we have arrived at what we set out to arrive. If this condition is true, if this condition here is true, if this condition holds, then that should hold. And we see here on the checking, with our choice of delta, which is epsilon over 3, our choice of delta here, placing it there, we notice that we obtain this expression, and manipulating this, we're able to arrive at what we wanted to arrive at, which is basically saying that the distance between our function and the limit is less than epsilon. So this shows that the choice of a delta is actually correct. So if you would want to come back here and you'd say, we're now choosing our delta to be exactly equal to epsilon over 3. That choice of delta makes this this condition achievable from that condition, as you've seen in the checking process. So this marks the end of my first video on Calculus 1. I'll see you in the next video. Goodbye.